Hello, and welcome to the April session of GeoStudio Tech Talk. These monthly webinars are designed to improve understanding of the software and ultimately promote success in your engineering projects. My name is Mark LeBeau, and I'm a research and development scientist with the GeoStudio engineering team at Sequent. This month's Tech Talk focuses on mastering three-dimensional analyses for groundwater flow in shaft and tunnel design. In this talk, we will briefly review different aspects of groundwater flow in shaft and tunnel design, introduce the workflow for modeling a stage-constructed tunnel, and present the best practice for mesh refinement in three-dimensional groundwater flow problems. Feel free to ask questions using the chat feature, and we will respond to these questions as soon as possible in a follow-up email. A recording of the webinar will be made available so participants can review the webinar again at a later time. First, let me introduce you to GeoStudio, in case you're new to our software. GeoStudio is a software package that has been designed for geotechnical engineers and earth scientists. The range of solutions and products allows you to solve a wide array of problems that may be encountered in these fields through practical, accessible, and rigorous numerical analysis. Today's webinar will focus on SEEP3D, a powerful finite element software product for modeling steady-state and transient groundwater flow through saturated and/or unsaturated porous media. Those looking to learn more can find an extensive library of resources on the GeoStudio website. There, you can find tutorial videos, examples with detailed explanations, and technical documentation for the background theory and features available in the software. As engineers and earth scientists, we generally follow an iterative design process that consists in asking questions, imagining solutions, planning designs, creating models and testing these models, and then making improvements. So what problem are we trying to solve? Well, let's imagine that our office has been mandated to design a 50-meter deep shaft and subway tunnel in an urban environment. The shaft, or doorway to the underground, must therefore be small but large enough to allow materials and machinery to enter and exit without issue. The soil profile at the site consists of a 10-meter deep sand deposit overlying silty sand with a shallow 5-meter deep water table. Now that we've defined the problem, we can brainstorm solutions and research ideas. In this case, the available space does not permit the construction of a circular shaft in which supports are in ring compression, but it does allow for the construction of a more efficient, space-saving elliptical shaft. Of the different construction methods, a slurry wall was found to be best suited for dealing with the groundwater conditions in the depth of construction, while a horseshoe-shaped tunnel boring machine, or TBM, was found to be well suited to the construction of the tunnel. The problems associated with groundwater flow, such as inflow, boiling, and heaving, will be dealt with using a combination of eductor wells, which use the Venturi principle, passive relief wells, and sub-pumps. After sketching several ideas, we've sent an initial design to our drafting team. Once the plans are ready, it's up to us to create a model that aligns with the design requirements and constraints, and improve the model if needed. So, let's go ahead, open the software, and create a new project. Although we could set up the analyses haphazardly, I strongly recommend following a 5-step numerical modeling methodology that consists in, firstly, idealizing the physical system, and thereby defining the geometry and the geology. Secondly, selecting the appropriate physics, i.e. the governing partial differential equations and the constitutive models. Thirdly, defining the boundary conditions. Fourthly, solving the analyses. And finally, interpreting the results. So, let's start by adding a three-dimensional geometry to our file. Once it's completed, we can open the three-dimensional editor and start creating a 10-meter deep sand layer overlying a 90-meter deep silty sand layer with an elliptical shaft in the center of the domain. The first step in the process consists in sketching the outline of the soil mass onto the XZ plane. Although the outline can be sketched to the exact dimensions, I find it much easier to sketch things very roughly and edit the points afterwards. Once this is done, we can extrude the sketch downwards by 10 and 100 meters. The second step consists in creating the initial phreatic surface, or water table. Once this is done, we can imprint the surface onto the relevant external surfaces of the soil mass. Note that we have removed the imprinting tool. The third step consists in importing the step file that contains the shaft profile, which was provided by our drafting team. We must also remap the axes to those found in the software and edit the base point. Once this is done, we can extrude the sketch downwards by 50 and 60 meters. Now that we've created the solids for both the soil mass and the shaft, we can cut the shaft into the soil mass using the cut tool. Once this is completed, we can delete the bodies that correspond to the excavated portions of the sand and silty sand layers. The relief wells at the bottom of the shaft can be represented by empty cylinders that allow for a significant reduction in the number of elements. This can be done by sketching the cross-section of the relief wells onto a translated XZ plane, extruding the sketch downwards by 8 meters, cutting the wells into the soil at the bottom of the shaft, and thinking ahead to the meshing process, we can also increase the mesh density on the inner surfaces of the wells. The tunnel can also easily be created using the profile provided by our drafting team. On this point, it must be noted that the profile also contains a 1.5 meter thick mesh liner that will allow for increased mesh density around the tunnel. Extruding the sketch into the shaft and soil mass according to the construction sequence, and more specifically, the first 2 steps of the sequence, cutting the tunnel and mesh liner into the model domain, and thinking ahead to the meshing process, we can also increase the mesh density of the tunnel and liner. Once the geometry created, we can use the laws of symmetry to reduce the size of the domain down to 1/2 of its original size. This will significantly reduce computational time and can be done by sketching the limits of the model domain onto the XZ plane, extruding the sketch down to the bottom of the domain, and cutting the model domain out of the larger domain. Now that we've created the geometry, we need to generate the mesh by clicking on the Generate Mesh button. It's important to emphasize that this step is specific to our 3-dimensional products, in which meshing is done on demand and not automatically. As an initial trial, we can set the edge length to 5 meters using a predominantly hexahedral mesh pattern. Clicking on the OK button launches a meshing process, In this case, the meshing process takes 21 seconds and yields 83,362 nodes and 94,217 solid elements. A review of the mesh quality reveals that the elements are generally excellent in and around the tunnel due to the mesh liner and rather poor in the vicinity of the relief wells. This can be addressed by increasing the mesh density in the soil mass at the bottom of the shaft. In so doing, the elements are found to be good to excellent in the regions of interest. We're now ready to close the editor and move on to the second step in the numerical modeling methodology, which consists in defining the physics or analyses of interest. In this case, we want to evaluate the effectiveness of the passive relief wells in controlling groundwater flow, and more specifically, the problems associated with groundwater flow towards the base of the excavation. This can easily be done by clicking on the Define Project button at the top of the Project Explorer, adding a steady-state seepage or SEEP3D analysis, and renaming the analysis for clarity. We also need to define the constitutive models or material properties of the sand and silty sand. This can be done by opening the Define Materials window and adding a material named sand. We can then set the material model to saturated unsaturated and click on the ellipsis, the three dots, to define the volumetric water content function, which is herein estimated using the sample sand material. Once this is completed, we can close the dialog box and select the function from the drop-down menu. We can then click on the ellipsis to define the hydraulic conductivity function, which is estimated using the Friedland-Xing-Huang model with a saturated hydraulic conductivity of 10 to the power minus 6 meters per second. We can then close the dialog box and select the function from the drop-down menu. Once this is completed, we can repeat the process for the silty sand, adding a material named silty sand, setting the material model to saturated unsaturated, clicking on the ellipsis to define the volumetric water content function, estimating the function using the sample silty sand material, closing the dialog box, and selecting the function from the drop-down menu. The hydraulic conductivity function can be defined by clicking on the ellipsis, estimating the function using the Friedland-Xing-Huang model with a saturated hydraulic conductivity of 10 to the power minus 8 meters per second, closing the dialog box and selecting the function from the drop-down menu. Once this is completed, we can move on to the third step in the numerical modeling methodology, which consists in defining the boundary conditions. This can be done by opening the Define Boundary Conditions window and adding a total head boundary condition for the water table at the far field. We must then add a total head boundary condition for the passive relief wells, and more specifically, the elevation of the sump. And finally, we must define a potential seepage face review boundary condition to allow water to leave the domain through the base of the excavation. Let's now reopen the editor and ascribe the material properties to the relevant solids and the boundary conditions to the appropriate surfaces. The sand is ascribed to the solid at the surface of the domain, while the silty sand is ascribed to all other solids except for those associated with the shaft. The water table is ascribed to the relevant external surfaces of the domain, while the passive relief well boundary condition is applied to the inner surfaces of the wells, and the potential seepage face is applied to the ground surface at the base of the excavation. We're now ready to close the editor and move on to the fourth step in the numerical modeling methodology, which is undoubtedly the easiest step as it consists in clicking on the Solve button. Solution of the finite element equations is surprisingly fast and takes less than 15 seconds on my mobile workstation with an 11th generation Intel i7 processor with 8 cores and 16 logical processors. Now that the analysis has been solved, we can move on to the last step of the numerical modeling methodology and have an in-depth look at the results. But before we do so, let's close the grid and the edge painting. The software provides the ability to generate contour surfaces of several different variables, including, but not limited to, total head, pore water pressure head, conductivity, volumetric water content, and so on and so forth. Let's start by having a look at the total head contour surfaces. As with any fluid, water flows from regions of larger total head to regions of lower total head. In this case, the total head is largest at the far field, where water enters a domain, and smallest along the passive relief wells, where water leaves a domain. Adding a clipping plane and scrolling along the x-axis provides additional insight into the shape of the contour surfaces. As expected, the head loss is largest as water moves upwards towards the base of the excavation. This warrants further investigation as it may lead to boiling at the base of the excavation and heaving of the entire mass between the base of the excavation and the base of the shaft. So what exactly is boiling and heaving? Well, to answer this question, we need to toggle back to the slides and return to the basics. The conditions that lead to boiling can be defined by considering a point in a saturated soil sample with upward groundwater flow. As shown in the bottom right-hand side of the slide, the point B, is in the middle of the sample and the head loss across the sample is equal to delta H. Note that the head loss is negative as it follows a standard physics convention that fluids flow from regions of high total head to regions of low total head. As most of you know, the effective stress at point B is equal to the total stress at point B minus the pore water pressure at point B. In this case, the total stress is equal to the product of the unit weight of the soil and the depth of the point of interest, while the pore water pressure is equal to the hydrostatic pressure plus the pressure associated with the groundwater flow, and more specifically, the fraction of head loss between the top of the sample and point B. If we expand the last term and regroup the first two terms of the equation, we find that the effective stress is equal to the effective unit weight of soil times the depth of the point of interest plus the product of the unit weight of water and the fraction of head loss between the top of the sample and point B. The boiling condition occurs when the effective stress is equal to 0. In applying this constraint, we find that the critical gradient, delta H over D, is equal to minus the effective unit weight of soil divided by the unit weight of water. Using a soil phase diagram, we find that the effective unit weight of soil is equal to the unit weight of water times 1 minus porosity times the specific gravity minus 1. Upon simplifying the equation, we find that the critical gradient is equal to minus 1 times 1 minus porosity times the specific gravity minus 1. In this case, the porosity is equal to 0.35 and the specific gravity is equal to 2.65. It therefore follows that the critical gradient is equal to minus 1.07, which is very close to minus 1. It must be noted that this equation is only valid for upward groundwater flow in cohesionless soils. The gradients reported in the software will therefore need to be compared to this critical value, but before we do so, let's define the conditions that lead to heaving. As previously noted, the effective stress at point B is equal to the effective weight of the soil times the depth of point B plus the unit weight of water times the fraction of the head loss between the top of the sample and point B. The effective force associated with the effective stress can be computed as the product of the effective stress and the surface area perpendicular to flow, which is shown in the bottom right-hand side of the slide. Moving the depth of the point of interest out of the parenthesis and dividing by the volume of the soil sample, D times A, yields the effective force per unit volume. The first term on the right-hand side of the equation is the downward force associated with the weight of the soil, whereas the second term is the upward seepage force, which is sometimes referred to as a drag or shear force. These forces are crucial in defining the conditions that lead to heaving. According to Terzaghi, the volume of soil associated with heaving is related to the depth of embedment D and normally extends half the depth of embedment from the wall or shaft. The forces at play are the downward force associated with the soil mass and the upward seepage force. The factor of safety against heaving failure is simply the ratio of these forces, and more specifically, the effective unit weight of the soil divided by the product of the unit weight of water and the mean gradient, delta H over D. The negative sign accounts for the fact that seepage force is negative for upward flow. It must be noted that the equation is equal to the critical gradient divided by the mean gradient, delta H over D. As shown in the bottom right-hand side of the slide, the total head at the bottom of the soil mass is not constant. This must be accounted for when computing the factor of safety. So let's toggle over to the software, evaluate the relevant gradients, and compare them to the critical gradient. To do so, we must first move to the definition view, open the editor, move over to the mesh view, suppress the clipping plane, and define the location of interest. Given that boiling is most likely to occur at the base of the excavation, let's define a profile at the center of the shaft, starting from the base of the excavation and ending at the base of the domain. Once this is completed, we can move back to the results view, open the Draw Graph window, and draw the vertical gradient profile. A quick look at the results reveals that the gradients near the base of the excavation are equal to minus 1.3 and therefore exceed the critical gradient of minus 1.07. This issue, or weakness of our design, can be addressed by increasing the shaft embedment depth and or increasing the length of the passive relief wells. These options, or scenarios, can easily be evaluated by moving back to the definition view, cloning both the geometry and the analysis branch, and renaming the geometry and the analysis. Note that we could have edited the same model, but this would not have allowed us, or our reviewer, to track our modeling process. Once it's completed, we can open the editor, improve our design. In this case, we'll increase the length of the shaft by 5 meters, and remesh. It should be noted that this and any further meshing and solving processes have been edited out of the presentation due to time considerations. We can then close the editor and solve the analysis. Once this is done, we can reopen the Draw Graph menu and review the vertical gradient. Although the gradient near the base of the excavation is now equal to -1, and thus smaller or less negative than the critical gradient, it remains quite high and warrants further action. So let's move back to the definition view, clone both the geometry and the analysis branch of our latest model, and rename the geometry and the analysis. Once it's completed, we can open the editor, make additional improvements, this time increasing the length of the passive relief wells to 20 meters, and remesh. We can then close the editor and solve the analysis. Opening the Draw Graph menu reveals that the vertical gradients near the base of the excavation are now equal to -0.2, which is well below the critical gradient. Let's now turn our attention to the potential for heaving of the soil mass between the base of the excavation and the base of the shaft. To do so, we need to determine the average value of total head on a surface, and more specifically a portion of a surface, at the embedment depth. This can be done by opening the editor, moving over to the mesh view, and defining the location. Once it's completed, we can move back to the results view, open the Draw Graph window, and have a look at the total head data at the edges of the surface. As expected, the total head is quite high, in the range of -34 meters near the shaft, and rapidly drops off to values below -38 meters within a meter from the shaft. We can therefore safely consider that the average value of total head is below -38 meters and that the factor of safety is well above 1. We can now focus our attention on the stage-constructed tunnel for which the internal components, or future voids, appear as meshed items in the domain. This is paramount as it provides the same mesh in all parent and child analyses. As will later be shown, the material assignment can be removed from the relevant solids during the tunneling process. So let's move over to the definition view and add several analyses to our analysis tree. In this case, we want to model groundwater flow into the tunnel as we breach the shaft. This can easily be done by clicking on the parent analysis, adding a transient seepage or SEEP3D analysis, renaming the analysis for clarity, and moving over to the Time tab to define the time stepping scheme. We can also model groundwater flow into the tunnel as the tunnel boring machine progresses into the silty sand material. This can be done by clicking on the child analysis, adding a transient seepage or SEEP3D analysis, and renaming the analysis for clarity. Once this is completed, we can remove specific material assignments and ascribe a potential seepage face review boundary condition to the surfaces where water is expected to leave the domain. This can be done by opening the editor, moving over to the first analysis, ascribing the boundary condition to the face of the tunnel, and then toggling over to the second analysis, removing the material assignment from the excavated portion of tunnel, and applying the boundary condition to the external surfaces and face of the tunnel. We're now ready to close the editor, move over to the Solve Manager, toggle on the analyses, and solve. Now that the analyses have been solved, we can have an in-depth look at the results. Toggling over to the first analysis, closing the grid and the edge painting, and removing and more specifically changing the opacity of the excavated shaft, reveals a significant drop in total head as water flows into the tunnel. Toggling over to the pore water pressure head contour surfaces reveals that the potential seepage face review boundary condition has set the pore water pressure head equal to 0 on the tunnel face. A very similar response is observed when toggling over to the second analysis, in which water enters through the surface and face of the tunnel. Although these contours and vectors are great, we need to have a closer look at the amount of water entering the tunnel. To do so, we must first move to the definition view, open the editor, move over to the mesh view, and define the locations of interest. In this case, we're interested in the face of the tunnel in the first analysis and the tunnel surface and face in the second analysis. This can be done by toggling over to the first analysis, changing the opacity of the shaft, and selecting the face of the tunnel, and then moving to the second analysis, changing the opacity of the tunnel segment, and selecting the surface and face of the tunnel. Once this is completed, we can move back to the results view, toggle over to the first analysis, open the Draw Graph window, and plot the cumulative volume of water entering the tunnel, and more specifically, the sum of the cumulative volume of water entering each node of the tunnel as a function of time. In this case, the cumulative volume of water entering the tunnel is equal to 0.44 cubic meters per day, which can easily be dealt with using low capacity pumps. Toggling over to the second analysis, and plotting the cumulative volume of water entering the surface and face of the tunnel, reveals that the cumulative volume of water has increased to 1 cubic meter. It therefore follows that the inflow rate has increased to 0.56 cubic meters per day, which is somewhat proportional to the increase in surface area. So we've had a look at inflow, boiling, and heaving, but what is the impact of the underground structures on the water table? Well, this can rather easily be evaluated by toggling on the water table, and more specifically, the isosurface corresponding to a pore water pressure of 0, and adding contours. As expected, the underground structures lead to a small, but nonetheless significant, 0.6 meter drop in water table elevation. Once this stated, however, it should be noted that the analyses did not account for surface recharge. In this webinar, a demonstration of groundwater flow and shaft and tunnel design was presented. A workflow for modeling stage-constructed tunnels was introduced, and a simple and efficient mesh refinement approach was presented. We've now reached the end of this webinar. A recording of the webinar will be available to view online. Please take the time to complete the short survey that appears on your screen so we know what types of webinars you're interested in attending in the future. Thank you very much for joining us and have a great rest of your day. Goodbye.